So, Chapter 2, Part 6. Let's start talking about organic chemistry. As I said earlier, organic chemistry is carbon-containing molecules because having carbon in a molecule actually allows us to make very big, complicated molecules. So carbon is unique in that it can form 4 covalent bonds with neighbors. Carbon is at position 6. So its first ring of electrons has 2. Its second actually has 4 for our perfect number of 6, right? Which means I can share with up to 4 partners, and they don't even have to be the same partners. That's actually a pretty unique quality to have. There are 2 mechanisms that allow for the formation of a wide variety of molecules. One, I can make carbon chains. I can actually make these carbon backbones that can be thousands long if I want them to. As well, it can either be hydrogen or oxygen or iodine. There are a lot of things that can actually be attached to this carbon. It doesn't necessarily just have to be one thing. And with that in mind, it also means that it can change the shape of that backbone, okay? So, carbon-containing molecules are essential to living organisms. Carbon-containing molecules that are essential to the lives of living organisms. Carbohydrates, lipids, protein, nucleic acids, and adenosine triphosphate. All of these are essential to keep you alive. So let's talk carbohydrates first. Carbo, atom, hydrates, hydrated. Carbohydrates can range in size from being very small to very large. Monosaccharides. Mono means one. So these are the simple sugars. These are the small sugars. Disaccharides. Di means 2. These are a little bit more complex. Polysaccharide. Poly means many. These are the complex sugars. They are made up of carbon, hydrogen, and oxygen in a 1:2 to 1 ratio. So when you look at glucose, our blood sugar, C6H12O6, if you divide by the lowest common denominator, if you divide by 6, you would have 1:2 to 1, because 6 divided by 6 is 1, 12 divided by 6 is 2, 6 divided by 6 is 1. So when I say it's a 1:2 to 1 ratio, that's what I mean. So the functions of carbohydrates, the functions of carbohydrates, the functions of carbohydrates. Do you think it's important? I hope you realize it is. So, 1, they're structural. I know most people think of carbohydrates as giving you energy, and while that is a big part of what they do, they are also part of the girders of the building in your DNA, your RNA, and your ATP. I'm sure DNA, you've heard it called deoxyribonucleic acid, deoxyribose, and RNA, ribonucleic acid, ribose. These are sugars, and they are sugars that are part of the makeup of your DNA and your RNA, and they have nothing to do with providing energy. They're literally part of the framework of those 2 molecules. So they're structural. Energy. This is the one I think everybody thinks of when they think of carbs. Simple sugars, the monosaccharides, can be used as an immediate energy source. Yes, we can consume complex sugars, but we have to actually process them into the simple sugars before we can use them. Glycogen is actually an important polysaccharide for us because it is basically an animal storage form of sugar for us. And then finally, the last function is bulk. Now you might be going, what? Okay. Cellulose is also a polysaccharide. It is a complex sugar, but this particular complex sugar, our bodies cannot process. I'm sure you've heard of fiber. Cellulose is fiber, okay? So you've got this very complex sugar that we do tend to eat quite a bit of, and our body can literally do nothing with it. So what happens? It creates the bulk of our fecal material. It makes our poop. Now I know you're probably going, ew, gross, but the more material we have in our intestine when we go to the bathroom, the easier it is for us to go to the bathroom. So if you have a ton of fiber in your intestine, it makes it a lot easier for you to go to the bathroom. So it does make the bulk of your fecal material in the fact that we can't use it. So mono means one, saccharide means sugar. Usually the monosaccharides have between 3 and 6 carbons in their makeup, but the two that we are the most concerned with are the 6 carbon ones and the 5 carbon ones, okay? So the 6 carbon sugars are the ones that are the most essential to humans. We have fructose, we have glucose, and we have galactose. Now, the chemical formula for all three of these is C6H12O6. That's what you write down for this, and for this. Now that may seem confusing, but think about it this way. If I handed everybody in the class 6 red Legos, 12 yellow Legos, and 6 blue Legos, what are the chances that everybody in the class would build the exact same thing with those Legos? Probably pretty slim, right? Unless you guys just all discussed it, there's no way that you guys would be building necessarily the same thing, the same pattern. It's kind of the same here. While I have the same building blocks, how they're put together varies. If you look at fructose especially, fructose is a 5-sided sugar. Glucose and galactose are 6-sided. That right there tells you, yeah, they're different from each other. They look different, even though, like I said, their building blocks are the same. They are isomers of each other. Remember, iso means the same. So while they have the same chemical pieces, they don't look exactly the same. These are the ones that are essential to humans because this is where we get our energy, mostly from glucose, okay? The two important 5-carbon monosaccharides are going to be the deoxyribose and the ribose. I just talked about these. Ribose and deoxyribose are part of our nucleic acids. Deoxyribose is specific to DNA. Ribose is specific to RNA. The disaccharides. Di means 2, saccharide means sugar. We've got sucrose, lactose, and maltose. Now, think back. We just talked about our monosaccharides, right? So sucrose, this is what we have that we put in our iced tea and we put in our coffee. It's a combination of glucose and fructose. So it's 2 monosaccharides coming together, di-2-saccharide. Lactose, this is the sugar that you find in milk that some people don't do well with. That's lactose intolerance. That is glucose and galactose put together. Just like you see here, here's glucose and fructose. You put them together and you've got sucrose, same thing, except it's glucose and galactose instead of glucose and fructose. Maltose is actually 2 glucose molecules put together. So maltose, if you've ever had a malted milkshake, that's maltose. They put maltose in that. If you've ever had Whoppers, the candy Whoppers, that kind of burnt sugary taste, or robin's eggs at Easter, that's maltose. That's what that tastes like. Now, polysaccharide. Poly means many, saccharide means sugar. You've got a whole bunch of monosaccharides bound together to form fairly long chains, okay? This is like a piece of one of those, okay? It can be straight, it can be branched, but it's a lot of those monosaccharides put together. There are three major functions and major types of polysaccharides. In animals, you really only find one, and that's glycogen. Glycogen can also be called animal starch. You know how potato plants make potatoes as a way to kind of store away their sugar? Potato plants don't make potatoes for us, they make them for themselves. We have something a little bit similar. So, glycogen is an energy storage molecule in animals. Now, this is the catch. Potato plants can put potatoes in the ground for months at a time. Glycogen is something that stores for a few hours. It's not something that stays forever. If we need to store that much energy for a long period of time, we'll convert it into something else. Glycogen, so let's say this morning for breakfast, I had pancakes and I had syrup with my pancakes, right? Okay, I ended up with a surplus of sugar. So let's say I had one pancake with a tablespoon of syrup. Some of that sugar will basically get broken down and put directly into my blood so that I can use it as fuel right then and there. But since I have a surplus, my liver is going to start converting that surplus into glycogen. Now, everybody knows that feeling of you're going good, you've got enough energy, you're doing great, and it gets to around, let's say, 9, 10 o'clock in the morning, and you kind of feel that, oh, man, I'm so tired. But about 20 minutes later, it's like you get your second wind. This is why. So, glycogen gets made and stored in your liver. So, when you eat in the morning and you've got that fresh supply, that excess gets stored in the liver. And when you hit that lull in the morning, your liver starts breaking that glycogen down to bring your sugar levels back up. And that second wind that you have is actually this storage molecule getting used right then and there. It is not something that will be there months later. This is something to store for a few hours and you're done. Okay? Starch and cellulose are plant specific. These two polysaccharides you find from plants. Starch is long chains of glucose used for energy storage in plants. Now, this is kind of the cool thing with starch. We can actually take advantage of that. We eat potatoes, we eat rice, we eat wheat. These are starch storage molecules from plants that we can consume and get energy from. Yes, we have to break it down and turn it into a monosaccharide, but we can still use it. Cellulose is different. So, cellulose is long chains of glucose that function as a structural molecule in plant. So, starch is their energy storage. Cellulose is their structure. It helps them to make their cells. Now, this is the problem. We can't break it down. We can't do anything with it. We can't use it for energy. We put it in our body and our body goes, so what exactly do you want me to do with this? 'Cause I got nothing. We don't have the enzymes necessary to break this down into a usable form of energy. So when our body starts processing it, it basically just lets it go through. And as it lets it go through, it becomes the bulk of our fecal material. That's why we talked about one of the functions being bulk, because this actually works as the bulk of our feces because our body literally can't process it. Okay, switching gears, let's talk lipids. Lipids is a very fancy way of saying fats. The major components for lipids are still carbon, hydrogen, and oxygen. Some minor components, depending on which lipids you talk about, include phosphorus and nitrogen. Now, compared to carbohydrates, lipids have a lower ratio of oxygen to carbon. So it's not the 1 to 2 to 1 ratio. It's more like a 1 to 2 to half ratio, okay? What that ultimately means is it makes them less polar, okay? It means that if you put Crisco or oil into water, it's not going to dissolve. It doesn't have the same charge quality that water does. If you want to dissolve this, let's say you get Crisco on something, you're going to have to use another type of solvent. So you'd have to use like acetone or alcohol. There are 4 groups we're going to talk about: the triglycerides, the phospholipids, the steroids, and then we're going to talk about kind of this other small group. So the functions of lipids, the functions of lipids, the functions of lipids, the functions of lipids, the functions. Do you think it's important? 1, protection. When you were little and you were learning how to rollerblade or roller skate, you remember your mom like put a pillow on your butt so that if you fell, the pillow took the brunt of the fall and not your butt? Same thing. We have certain organs that are surrounded by lipids. And the reason that they're surrounded is because it's a pillow. It pads that organ. One of the best examples is our kidneys. Our kidneys actually sit slightly below our rib cage. So part of our kidney is covered by a rib cage, but then the other half is kind of hanging out below. That means that if something comes and hits me in the back really, really hard, there's a good chance that it would rupture a kidney. So what do? Well, we pad it. We put a fat pad around our kidney so that if I'm backing up and I accidentally like bump into a podium, I'm not going to bleed to death. Instead, the fat takes the bulk of that trauma. 2, insulation. Fat under the skin prevents heat loss. Now, everybody knows the skinny kid and the fat kid, and the skinny kid's always cold and wearing sweaters in, 90-degree heat in summer in South Texas, and the fat kid's always like, oh my gosh, it is so hot. I'm the fat kid, just FYI. I'm always warm. So we have, as bigger people, more fat reserves in our body under our skin, and it kind of acts like a styrofoam cup. It helps our body to hold on to heat, which actually works really well when it's cold outside, but when it's warm outside, it kind of sucks. Okay, myelin sheaths are also made out of lipids. They electrically insulate your neurons. So think of an extension cord being covered in rubber, right? The rubber on the extension cord actually electrically insulates the wires in that extension cord. This is kind of similar, except instead of a wire, it's actually one of your neurons, one of your cells in your body. Regulation. Steroids. Steroids regulate physiological processes. Prostaglandins regulate inflammation. So testosterone is an example of a steroid. Testosterone is in charge of making little boys turn into men. It's in charge of making your voice go deeper and your skin's change in texture slightly. Your musculature changes. You get the big barrel chest. You also get more hair on your body than women do. For women, we have estrogen and progesterone that are also steroids that help us to go through our menstrual cycle and help us to develop the lining of the uterus, prepare an egg for release, and prepare our body for pregnancy. These are regulatory physiological functions that our body has, and they're being controlled by those lipids, those steroids. Vitamins. We talk about fat-soluble vitamins because they have the characteristic of a lipid. They follow the same characteristics. To give you examples, because there are tons of vitamins that do tons of different things. Vitamin A is used in your eye to make something called retinol. Retinol is what helps us to have night vision. Vitamin D actually promotes our bodies to absorb calcium into our bone. Vitamin E promotes healing, not in the sana kind of way. I know everybody's like, sana. Yeah, no. It isn't your Thea telling you to go and get vitamin E tablets and cut them open and put them on your skin. That isn't it. Vitamin E is used to make one of the fibers in our skin called collagen. When you have a lot of vitamin E, you can make a lot of collagen, and it's a little bit easier to heal wounds. Vitamin K is actually necessary to form clotting factors. Back in the days of the Depression, one of the rash of things that happened during the Depression was women were giving birth, and within a few hours, the babies would hemorrhage to death, and usually mom would too. And it took a while to figure out that during the Depression, people weren't eating. So they weren't getting dietary vitamin K. So one of the common practices that started during the Depression was babies born, you give them a shot of vitamin K and they're healed right then and there. To this day, they still kind of do that. Fifth function for lipids, structure. They form the phospholipids and cholesterol in your cell's membrane. Each and every individual cell in your body has a cell membrane, and it's made out of phospholipids and cholesterol, both of which are types of lipids. If you don't have cells, you don't have a body. And finally, energy. It can be broken down to yield energy. And to be honest, it's about twice as much energy as what you get from carbs. Pound per pound, you get twice the amount of energy from lipids than you do from carbs. The one problem is your body prefers carbs to get its energy because it's easier. So, triglycerides. What does tri mean? Tri means 3, right? 1, 2, 3. Glyceride. Here's a glycerol. You've got a glycerol with 3 fatty acid tails, okay? It makes up about 95% of fats in the human body. You got the 1 glycerol, the 3 fatty acids. Now, the fatty acids themselves differ in whether they are saturated or unsaturated. So if you look at this chain of carbons here, saturated basically means that every carbon has 4 partners. So I've got 4 partners for this carbon, 4 partners for this carbon, 4 partners for this carbon. And 4 for this carbon, just to kind of keep it out of the way of that menu. Saturated means I have 4 partners for every carbon in a chain. This type of fat is actually not healthy for you. This is the type of fat that causes like heart disease and things like that. Unsaturated means somewhere in that chain, you will have a double bond. So here's 1 carbon, here's another carbon, but there's a double bond here, meaning instead of having 4 partners, they will have 3. Okay, so 1, 2, 3. Monounsaturated means that you have 1 double bond. Polyunsaturated means that you have more than 1. You can tell monounsaturated fats usually because at room temperature they are liquid. Crisco is not an example of a monounsaturated fat because it's solid at room temperature. Trans fats. Trans fats are not something that you should hear about a lot. Chemically, they're altered fats that were discovered to extend the shelf life of food. The whole reason that they started kind of coming into common practice was because they gave things a longer shelf life at the grocery store. But after a certain amount of time, it was also figured out that trans fats were even worse causing heart disease than the saturated fat. So in 2000, I don't remember what year it was. I want to say it was 2003. They said no more trans fats in anything. You've got to take it out of all of your products. And you have 5 years to get it done. And by 2018, nothing should have trans fats in it anymore, basically on the market, unless it's naturally occurring. So now one of the big advertisement things is no trans fats. The thing that I find funny is that some of those things never had trans fats to begin with, like Cocoa Puffs. No, trans fats. It never had fat in it. It was all sugar. So, but people will buy it because it says it. Phospholipids. Phospholipids are similar to your glycerol in the fact that you've got tails and you've got a glycerol group, but you've got only two tails and you've got this phosphorus containing group here. So you've got the head and you've got two tails. Structurally, like I said, they're kind of similar to triglycerides, but they're also polar, meaning one part loves water, one part hates water. Okay? They are essential to a membrane structure, and the way that they are put into a membrane, you have this phospholipid bilayer with the water hating part in the middle and the water loving part on the outside of your cell and on the inside of your cell. Now you might say, okay, why is that important? Because it kind of gives us a bouncer between what is allowed to go into and out of our cell. If there is something that really likes water and it just tries to go through, the tails will spit it out because the tails don't like it. And we'll discuss that more in chapter 3. Steroids. Structurally, they are a very unique lipid. Every other lipid that we've been talking about is a chain of something. These are rings, okay? The steroids are usually derived from cholesterol. So this is cholesterol, this is bile salt, this is estrogen, this is testosterone. You've got this 4-ring structure. Cholesterol, like I had said previously, is a building block for the cell membranes, or is a part of the cell membrane and a building block for the other steroids. Now, there's a balance though. You can't just ingest as much cholesterol as you want. If you ingest too much, it can actually cause heart disease. So again, you've got bile salts that come from that: estrogen, progesterone, testosterone. Now, our other category, eicosanoids. These are molecules derived from fatty acids. One of the things that makes them kind of interesting is almost every cell in your body makes them, and they're important in regulatory functions in your body. One of the best examples is blood clotting. Where might you need to clot your blood? Anywhere. It just depends. If I cut my finger, if I cut my leg, if I'm bleeding internally, I need to clot my blood wherever that is. So all of my cells being able to create these eicosanoids is important. Those fat-soluble vitamins that we were talking about earlier, structurally, they're not really similar to one another, but when you look at their characteristic of being a nonpolar molecule, that is like a lipid, and you have to have them for your body to function normally. If you don't, your body doesn't work the way that it should.